Now let me share my screen. Okay, you should be able to see the worksheet shared now. There's also a link in the chat in case you didn't see it. Okay, let me. Make sure I can see chat. Okay. Great. All right. So, cool. All right. So I was thinking we try to get through the first 4 out of 5 problems. The last one's pretty tricky. As always, there's a full solution for each problem on the GitHub page. But yeah, that's the plan. So let's start with the first one. So here we have types A and B. So the first part asks us to assume that both A and B are propositions. And from that assumption, we want to prove that the coproduct A plus B is a proposition if and only if this implication holds. If A, then not B. Now, conceptually, this is kind of interesting because you might have hoped that propositions are closed under coproducts, or in other words, disjunction. But it's not always the case. It needs to satisfy this condition. To fix that, we would need to take this coproduct and apply what's called the propositional truncation, which I think we'll be introduced to next time, I believe. But in any case, we don't have that yet, but I just wanted to point that out conceptually. Okay. So, cool. So let's do this first one here. So part 1, let's first suppose that A plus B is a prop. And we want to show the implication. So to show, so if we want to show A, then not B, let's unfold this to see that what we need to show is if A, then we get an element of this function type. If B, then empty type. So, okay, so we'll proceed by taking an arbitrary element of A and then an arbitrary element of B, and we want to construct an element of the empty type. Now, how are we going to, so we're probably going to want to use our assumption that A plus B is a prop. What's one meaning of this assumption? You might remember from lecture that a convenient meaning of this statement is that for all S and T in the coproduct, we have that they're equal. So how can we use that to get an element of the empty type here? Well, we have an element by hypothesis of A, an element by hypothesis of B. Now, we want to recall that we have this property of disjointness of coproducts, which I think was proved or mentioned a couple lectures ago. And we do that through the observational equality method that we've seen for natural numbers and Booleans, at least. And so, all right, so once we recall that, we'll see that if we, if we form an identity type in the coproduct using the elements from A and B that we have, then we could consider this disjointness property that I mentioned. From that, we can see that once we have an element of this identity type, then we can get an element of the empty type. In fact, I mean, the observational equality method showed that this type is in fact equivalent to the empty type. So we have this function, but okay, so now we want to know, do we actually have an element of this identity type? Yeah, we do, because this lives in the coproduct, and we've said that we have this fact to work with from the assumption that A plus B is a prop. So indeed, we do get an element of the empty type, which proves the first direction. Okay, so let's see. So the next direction is taking this implication and proving that A plus B is a prop. Okay, so I'm going to move on to the next page. So the converse says that we should first suppose. Oh yeah, and notice before I move on, notice that we didn't specifically use that A and B are props for the first direction we proved, even though we still have that assumption in the background. All right, so suppose now that we have a function of this form. Now I want to, so to prove that A plus B is a prop, I want to again consider the definition of prop that I mentioned, which is that for any two elements of the coproduct, we want to show that those two elements are equal. So let's see. So now I want to show that for all S and T in the coproduct, we have that S equals T. So this will prove that it's a prop. Any ideas on how we could go about showing this, that we have an identity between any two elements? Notice the form of the statement we want to prove. For all S and T in this coproduct A plus B, we have S equals T. Yeah, pattern match on observation. Not exactly pattern matching on observational equality. We do hidden, I think what is correct in that suggestion is that we do want to pattern match somewhere, and pattern matching on observational equality would mean ultimately pattern matching on the coproduct. So I do agree that we should pattern match on the coproduct. Oh, I meant, okay, so you meant on S and T, correct, yeah. So perfect, so so another way of saying that is induct on, double induction on the coproduct, so induct on S and T. So, okay, so let's see. In the case, so when you double induct on a coproduct, you really have four cases to consider, right? So let's look at the case where so this is what we want. So now we want to prove four cases of an identity type. So let's have this first one here be of the form in left. Oh, let me give a better. It's cut in left takes elements from A. So to be a little more sensible, let me do A prime. Okay. Now I think now observational equality might come into play, as you were saying in the comments. Remember that this type is equivalent to the identity type in just A of A equals A prime. But so I want to prove, so so there's, so, okay, there's, so the form that I stated, being a proposition, the form in which I stated the property of being a proposition is that I want to prove an element of this. Yeah, and so to prove an element of this identity type, in left A equals in left A prime, and knowing that that entire identity type is equivalent to the identity type A equals A prime, what can I finally apply now to get a term of this type here? And again, let me make sure we have an equivalence between these two things. So we have functions back and forth in particular. So if I have functions, if I have an equivalence of types, and in particular functions back and forth, and I want an element of this type on the top, a natural thing to do would be to consider if I have an element of A equals A prime down here, and then I can apply the function in this direction to it to get an element up here. Do we have an element of the bottom type? If A and A prime are in the type big A. Yeah, so in the comments, yeah. So A is a prop, so exactly. So since A is a prop, we do have an identity here. We have a term of type A equals A prime. Okay, cool. So that's one case. The case for in right B equals in right B prime is exactly similar. Now we're going to do the same argument using that B is a prop by assumption as well. And then the other two cases are the in left in right and in right in left. But recall that those two cases give us identity types that are equivalent to the empty type. Right. So once yeah, let me okay, so yeah, let me just spell out one of the, so the in right case is exactly similar. Let's do one of the disjoint coproduct cases. Let's do in left A equals in right B. So we want an element of this type, but as I was saying, this type is equivalent to the empty type by our observational equality method from before. So we're going to need to get a contradiction, and that should indicate to us we're probably going to want to use somehow the assumption we haven't applied yet in this proof, which is that if we have an element to A, we have an element to not B. But that's not too bad, right? Because we do have an element to A, right? We have this element A nested inside the in left. We have, so that we also have not B. And then finally, not B tells us that if we have an element to B, we do get an element of the empty type. And so then we'll use the element B nested in this in right. Yes, so we also have B in big B, which gives us the contradiction. Okay, so And then the in right, in left is exactly similar. So that proves our 4 cases. So, and that completes the first part. Are there any questions on this first part of problem 1? Okay, so let's move on to part 2. So part 2, going back up here, says that if we let K be any truncation level, so recall that this Blackboard T denotes the type of truncation levels. It's basically the natural number. It's basically the integer starting at -2. So now we're going to assume that A and B are both K+2 types. Okay, so this is really a theorem that starts at the 0 case and goes up. And then from that assumption, we're going to prove that the coproduct is a K+2 type as well. So notice that we didn't have this property with the case of -1, which corresponds to propositions, right? It's not the case that 2 propositions are closed, that propositions are closed under coproducts. But once you get to the 0 case and above, we do have this closure under coproducts for n types. Okay, so hopefully we'll remember the problem statement. So let me repeat that we have this arbitrary truncation level. This kind of looks like a pi type. So let me just write capital T. Okay. We also have that A and B are K+2 types. Okay. So we want to show that the coproduct is also a K+2 type. All right, so let's think. So we had that nice definition of being a proposition where any 2 elements are equal from before, but now it's a good idea, now that we're working on with general truncation levels, to use the generic definition of a K type when proving this. So what that means here is that we want to show that for any elements in the coproduct, the identity type between those 2 terms is a K+1 type. So that's what it means to prove that the coproduct is a K+2 type, is to prove that all of the identity types in it are K+1 types. Let's start, let me just get a new page. All right, so okay, so this is what we really want to prove. Now, again, just like before, we have this statement we want to prove that is of the form, for any 2 elements in the coproduct, blah, blah, blah. So as before, that should kind of scream, double coproduct induction, which in fact we will want to use right now. So let me say that by double induction on the coproduct, we again just have 4 cases to consider. So we want to consider four cases like this. Can people, I just was told I was signed out. Can people hear? Am I still visible and audible? Okay. Yeah, sorry, Zoom just told me that I'm signed out because my account is signed in from another device. So, okay, as long as I'm hopefully everything goes okay. I'll just ignore it. Okay. Okay. Anyway, okay, so let me continue. So we have these 4 cases. I wrote down 2 of them. Now let's see. Oh, okay, never mind. I thought I. Okay, so in left A, and then in right B, and then finally in right B, and in left A. Okay, cool. So so each of these 4 cases, what we need to show is that each is a K+1 type. So each of these 4 is a K+1 type. Okay, so let's consider these cases now. So we can break it down like before into 2 cases and then another 2 cases. So the first 2 cases, how can we know that these are K+1 types? So for the first one, let's again recall that this type is equivalent to the identity type A equals A prime in A. So okay, so now I guess I'm secretly asking everyone to recall the property that K types are closed under equivalences. So if a type X is a K type for any K, any truncation level K, and X is equivalent to another type Y, then Y is also a K type. So because of that property, it suffices to prove that this identity type A equals A prime in big A, is a K+1 type. How do we know that? How do we know that this right here is a K+1 type? And let me, to jog your memory, we might want to use some assumptions. So we had this right here. We had a truncation level, and then A and B are K+2 types as our assumptions. So any ideas on why A equals A prime is a K+1 type? Okay, just so remember that, so looking at these assumptions here, if A and B are K+2 types, by definition, that means that all of their identity types are K+1 types. That's what it means for a type to be a K+2 type. So because of that, it follows immediately, actually, that this identity type, A equals A prime, is a K+1 type. Because it's an identity type in big A, and big A, by assumption, is a K+2 type. Okay, so that case is done. The second case follows exactly in the same way from the assumption that big B is a K+2 type. Now, how about these bottom 2 cases? So remember now that we're in the disjoint case. So actually, these 2 identity types are both the empty type, equivalent to the empty type. So again, now we just need to show that the empty type is a K+1 type. Is the empty type a K+1 type? Yeah, so it is a K+1 type. And in particular, because it's we proved this in lecture, the empty type is a proposition. So the empty type is, recall, a -1 type, i.e. a proposition. it is indeed true that for all K truncation levels, the empty type is a K plus 1 type. Okay, so yes, so we're all set there too. So yeah, so that completes the induction, and yeah, and that's the closure under coproducts for K plus 2 types. Great. Any questions on problem 1 before we move on? Okay, so let's continue to the second problem. So the real reason I specifically want to cover this problem because as was pointed out on the Discord earlier, this problem uses the solution that you'll find on GitHub, and I guess the quickest solution for this problem uses a theorem that is stated and proved in the lecture notes that Emily posted on GitHub, but was not specifically covered or even mentioned in the lecture yesterday. So usually I wouldn't want to include a problem that wasn't touched on in lecture. So I do want to go over the solution here, and in particular the theorem I'm talking about from the lecture notes. So anyway, okay, so we fixed this universe U. It's, keep that in mind. This problem isn't about tricky universe things, but we have a universe U, a type, and we're going to assume that we have this partial order, which is this function from A to the type of types in the universe U that are propositions, okay? And partial order here means what it usually does, in the sense that we're going to have a proof that witnesses that it's reflexive. So there's going to so this is going to be a type that is with a proof. This is going to be a type equipped with a proof that it's a proposition, and we're going to have a term, because it's a partial order. We're going to have a term of this type, which witnesses that the relation is reflexive. And similarly, we'll have transitivity and, crucially, anti-symmetry. So in particular, you might be considering how this could be true. Let me finish the problem. So we have this partial order on a type A, and now we want to show that that's enough to conclude that A is a set. And as I was saying, you might wonder, how is that possible? Can't you come up with counterexamples using the circle or something by defining some partial order? I mean, defining some ordering on it. But the orderings you might come up with are not going to satisfy this anti-symmetry property. You can certainly get transitivity and reflexivity, but this anti-symmetry property is crucial. Okay, cool. So let me now go into, sorry. Let me go into the theorem I'm talking about in the lecture. So this, okay, so I believe that the latest version of the lecture notes have this on page 8 of lecture notes. So we have this, we're going to have this theorem that assumes a type A and a binary relation big R on A. And now we're just assuming that it takes values in the universe. It's not necessarily it's not valued in propositions necessarily. Okay, so now let's assume that we have 3 properties, that this relation satisfies 3 properties. so we are going to want each of them to be each R on X and Y to be a proposition. We are going to want R to be reflexive. And then finally, we are going to want there to be a map. Let's call it little f, that, well, actually, yeah, let's write it like this. Let's write it as a pi type. So we have this dependent function that for any X and Y in A, we are going to have a map from RXY to the identity type, X equals Y. Okay, so we're assuming that these properties are satisfied, and if that's true, then we can conclude that we have a term. Well, we have a term, a family of maps. Well, actually, sorry, that's not the right way to state it. So we so okay, there's a comment that asks, could we try to say that we have for every so when you say for every X equals Y, do you mean for every X and Y in A? Oh no, you do. Okay, so for every identity type. So for every identity type X equals Y in A, we have X is less than or equal to Y and Y is less than or equal to X are true. Yes. So I don't. So yeah. So we will have that X is less than or equal to Y and Y is less than or equal to X, and then we therefore can get an element of X equals Y, and then so I think so when we say that X equals Y is a prop, we well actually, all right, I don't want to, let me finish this statement and then I want to go back to this this question when we get to the problem. So yeah, sorry to stop the statement like that. So so that now so then for any family of maps of the form X equals Y to R XY. So any family of maps of this form is an equivalence. Okay. So in particular, that means that each identity type in A is equivalent to R to a proposition. So because this right here is a type that's a proposition by the first assumption. Okay. So because each of the identity types is a proposition, we can conclude that A is a set in this case. Okay. Okay, so I do want to mention that the proof is in the lecture notes, but the proof shown in the lecture notes actually goes to an argument that we've seen before on a previous worksheet, I think the last worksheet, which says essentially that if each of these maps on X and Y here, if each of these is a section of, okay, this is a little clumsy to say this way, sorry. Let me rephrase it like this. So really this problem in the worksheet, the last worksheet says that if a map, let's call it G, from X equals to Y to R on X and Y has a section, if if a map has a section for each, so for all X and Y in A, then G of XY is an equivalence actually. This was I can't quite remember the problem, but it was on the last worksheet. It was a consequence of actually it was the final part of one of the multi-part problems in the last worksheet. So if a map has a section for each X and Y, then we do get a family of equivalences. So using this fact, we can prove this theorem here pretty easily by just noting that if we take our map little f on each X and Y, we can see that it automatically is a right inverse of G here, right? And that's, that follows exactly because R is a proposition for X and Y by assumption. Okay, so we get a section immediately of little g for each X and Y, and therefore we have that it's each of these GXY is an equivalence. So that's the theorem. Okay, that was a little detour, but so let's go back to the statement. Okay, so we have this theorem that says we can conclude that a type A with a relation like this is a set, which we want in our problem 2 here, as long as we can construct, as long as we can prove yeah, okay, there's one final thing I realize that I need to mention here. This theorem says that we can conclude that any family of maps of this form is an equivalence, and therefore that A is a set, but that we only get a family of equivalences with propositions if we can actually find a dependent function like this. But we can in fact do that because by path induction, we do get a family. We can construct an element of this type, right? Because if X is the same as Y, then we need an element of RXX, but we have that by 2, R is reflexive. So we get that term. So anyway, that's why this theorem lets us conclude that A is a set as long as we can find a relation on it with these 3 properties, okay? So let's apply that here. We have a relation already, a partial order, but we can't immediately take that relation and use it as our R here in the theorem to conclude that A is a set. It is reflexive and it is valued in propositions, but this final part, 3, we don't have a way to prove that automatically, that there's a map of this form into the identity types. So okay, so the goal now is, let's construct find a new relation on A that satisfies the 3 properties. Okay. Now, I'm going to just, all right, let me get back to the comment. We don't, okay, so so in the comments, we have a question. Said another way, do we know that the binary product of S is less than or equal to Y and Y is less than or equal to X is equal to the type X equals Y? Or maybe we can even just say equivalent to at this point. All right, well, X is less than or equal to Y and Y is less than or equal to X is so both of those types are by assumption propositions because the partial order is valued in propositions. It's not too hard to see that the Cartesian product of those 2 things is also a proposition then. So if we knew this, if we knew that that binary product was equal to X equals Y, then we would know that X equals Y is a proposition. In other words, and since X and Y are arbitrary, we would then know that A, the type that X and Y live in, is a set. So we don't know that a priori. Okay, sorry, in the interest of time, since I'm running a little late, hopefully that answers part of that at least. Let me finish this up. So let's so find a new relation on X satisfying 1, 2, and 3. So it's a bit slick. We do. So here's the motivation. The property we really are missing and want to have is that we can find a map that takes an element of the relation that X is less than or equal to Y in this case, and says that X is equal to Y. Now, now I just said from the, responding to the comment that we don't know necessarily that X less than or equal to Y and Y less than or equal to X is equivalent to X equals Y, but we do know that if we have both of these relations, then we have a map to X equals Y. This is exactly what anti-symmetry is stating. So, and again, all we need at this point to apply the theorem is a map of that sort, or, is a map into the identity. We don't need an equivalence from the start. Okay. So what does that, so knowing that we have this property, what can we take our new, so let me call this new relation S, big S. What can I take what can I take my new relation to be? What type should I put here? And I want this new relation to be reflexive, to be a proposition for each X and Y, and to have a map into the identity types. Any ideas on what type to put here in this spot? So actually we can just put this right down here. So we, as we just said, this gives us the, okay, so X is, so from anti-symmetry, we have the third property, the map into the identity types. Do we have reflexivity? Yes. Is X, do we have a proof of X is less than or equal to X and X is less than or equal to X? Yes, because our original relation less than or equal to is reflexive by assumption. It's a partial order. And do we have, it's a proposition? Yes, because the Cartesian product of two propositions is again a proposition. Okay, so okay, so it's a little slick, but you can this trick of defining a new relation with X less than or equal to Y and Y less than or Y less than or equal to X does the job. Any questions on this one? Okay, I'm gonna continue to move on. Let's see. Okay, which one am I? Let me, I probably, this 4 is very short. It, who knows if we should definitely do 3. It's more interesting, but I guess if by a miracle we get through this really quickly, I can talk about 4 as well. All right, so let's do 3 though. Cool. All right, so let me zoom in a little bit. All right, now for the first one, we're assuming A is any type, but B is a set now. And we're gonna consider an injection in the sense that when f of x equals f of y, then x equals y. Okay, so from this data, we want to prove that f is actually an embedding. And then, okay, so if we prove that, then from a theorem covered in lecture yesterday, we can automatically conclude that A is a set as well. Oh wow, oh yeah. So A, when you have an embedding into a K-type, then the domain of the embedding is also a K-type. So we can apply that in particular to sets here. Cool. So remember that it's not always the case that injections between types are embeddings, but in the case that B, the codomain, is a set, it's enough. Okay. So let's so we want to show that F is an embedding. So for any X and Y in A, I want to show that this map here is an equivalence. Okay, cool. So, all right. Yeah, I see now. Okay, I now realize that I was the solution I gave. When you go to look, if you want, at the solutions, I did give a pretty slick solution to this first one here. And I realize it might be a little unenlightening at the moment. What I did was I again applied that result from the previous worksheet that I mentioned in the previous problem to conclude that F is an embedding. So here's what I did. So note that, so we have this term little c by assumption, right? This dependent function. So note that each of these little c's, each of these maps is a right inverse or a section of this function, this action of F. And the reason it's a section is because the codomain is a proposition. So when you have a composite of this form, then to prove that this composes to the identity is automatic, actually, because everything ends up in a proposition. So you do have a homotopy witnessing that this composite is the identity function. So that means that this is indeed a section of app F. And once you know that this map has a section for all X and Y, then it automatically follows that it's an equivalence for all X and Y. So I'm going to have to just direct you to this problem on the previous worksheet 7. And this is exactly the same idea that I was mentioning in the proof of the theorem from the previous problem as well. So yes, I will need you to maybe dig that up a little bit. So sorry about that. But that's why, so since it has a section for each X and Y, in fact, this map here is an equivalence, and therefore F is an embedding. So that's all I'll say about the first one, because I want to talk about problem 2. Okay, so, whoops. What do we have? Okay, so problem 2 says that we're going to consider this function from the naturals to the naturals, that takes in a natural and spits out the addition with M. And I'm assuming that this addition is defined by recursion on the first variable, which is not the same as the book, Egbert's book, which does it on the second variable. It makes things easier just to assume that it's on the first variable here. Yeah, so the first variable, first argument. Now, we want to prove that this is an embedding. So is an embedding. And from that, we want to conclude an equivalence that says that showing that M is less than or equal to N, where this relation is the relation on natural numbers that we defined a little while ago. So this has already been defined on natural numbers, is equivalent to saying that there's some natural k such that n plus k is equal to n. Isn't, yes, on natural numbers, correct. In the comments it asked, isn't this relation less than or equal to, on the natural numbers, valued in propositions? So each of these here is a prop. Yes, that's true. You can define that. You can prove that by induction, on double induction on the naturals. Okay, so let's get into it. All right, so let's start with proving that. So part 2, let's show that this map is an embedding. Okay, but the sigma type, all right, so we have a, so here's the interesting part. So there's a comment saying that, well, yes, we can see that the less than or equal to type here is a prop. But if we have an equivalence, then that would mean that this sigma type is also a prop. And yes, although, and you're right, that is not obvious at the start that such a sigma type would be a prop, but in this case, it is. It is. Okay, so that's an interesting result. So going back to this proof of the embedding, let's use induction on the natural numbers of, people hate how I write. Sorry, that's actually my Blackboard N, but it looks like a conjunction disjunction thing. So you know what? This is harder than it should be for me, but I think I'll just go like this. For the natural numbers, use induction on the natural numbers, specifically on this variable little m. So specifically on little m, and that'll be useful because addition was defined, like I said, on the first variable here, m. So that should do some good for us. Okay. So the base case, m is the same as, is definitionally 0. What that means is that m plus n is always going to be definitionally n. So this function here becomes the identity map on n, right? So the identity on the naturals is an equivalence and therefore an embedding. And you can just see it's embedding directly too. So the base case amounts to showing that this identity map is embedding, which is true. So let's go to the inductive step. Okay, so for the inductive step, the way I want to do this is I want to take equivalences that I already know hold, and okay, so let me be clear about what. So for the inductive step, I want to show that this. Oh, let me write that more clearly. How about I say, maybe it's clear if I go. So n will map to the successor. So big S is the successor here. Plus n. So so let me let, for any X and Y naturals, okay? We want to show that this is an equivalence. Okay, so we've assumed it for little m by induction, and we want to show for the successor case now that this is an equivalence for each X and Y. Okay, so now I know, so I'll know from the inductive step, I'll have an equivalence for app for little m here. And then I can also consider other equivalences that I know hold with certain identity types in the naturals that that form the domain and codomain of and really they'll form the domain of certain equivalent. I don't know if I said that's probably really. Let me restart. So I have this equivalence in I have an equivalence assumed in the inductive step for little m, but I also can form equivalences with certain identity types of the naturals, which will end up coming into play when trying to prove that certain app functions like this are also equivalences. So okay, let's see what that means. So let's start by looking at a triangle. So I have a map here, which is the app function for the successor on m plus x and m plus y. And then I have a couple other maps coming from the identity x equals y, and that will be an app that adds m to the argument, and then here, what I'm going to have is the function that we know something about, the app function that takes an argument and adds a successor of m to it. So let's think. So this map on the right, let's make sure it type checks. When I take successor of m plus x, for example, because I define by assumption addition on the first argument here, this computes to successor of m plus x. So indeed, this is the correct codomain. S of m plus x equals S of m plus y. So we have a triangle. Does it commute? Yes, it does. And the way to do it is if we want to show that here to here is the same as from here to there, we can use the fact that the domain will be, we can use the fact that the domain of the homotopy we need is the identity type x equals y, where x and y are arbitrary, and use path induction to prove this commutativity pretty easily. Okay, so we have this one triangle, and we know that by the induction hypothesis, we know that this left map is an equivalence. And we want to show here, this map is an equivalence. It will suffice to prove that the top map is an equivalence by the 3-for-2 property of equivalences that we have. So now to prove that this map is an equivalence, I'm actually going to want, the way I want to do it is form another commuting triangle up here and prove that the left arrow here and the right arrow here are equivalences, so that by 3 for 2, we again get an equivalence at the top. Okay, so which the type I want here? If you look at it, you might see there's a single type where this and this are both, where these two types both have an equivalence to it. And that will be the observational equality. Oops. Observational equality on n with m plus x and m plus y, m plus y. And remember these maps from our definitions. Remember that we have equivalences with, so we have an equivalence, m plus x equals m plus y, with the observational equality m plus x, m plus y, that we know there's an equivalence there. And we know that the same is true for successor m plus x equals successor m plus y on the observational equality for successor m plus x, successor m plus y. But remember, by our definition of observational equality on naturals, that this type right here is actually definitionally equal to the case on the two successors. Okay, so in fact we have equivalence. Both of these maps to their observational equalities are equivalences. Does it commute? Yes, it does. Yeah, it does commute. Yeah, okay, sorry. Yeah, so I was saying that this top triangle commutes as well. Okay, so from here to there is the same as going from here to there and then to there. That can be shown by considering. There's a subtle point here. I can't, unlike down here where x and y were arbitrary and I can immediately perform path induction to get the commuting triangle. Here, neither endpoint of this identity type is free. So I can't directly use path induction to prove the commuting triangle up here. So the technique you want to use is to generalize from m plus x to m plus y to just any two arbitrary elements of natural numbers, and then form the corresponding triangle with those two arbitrary elements, and then use path induction to prove that this triangle commutes. And then you can, after that, specialize to the m plus x, m plus y case. So there is a proof that the top triangle commutes as well, which as I explained before, gives us that this top one is an equivalence, and therefore this is an equivalence, which is what we needed for induction. Okay, so there's a second part to the problem. So let me get through that as well. So that proved that this is an embedding. We want to conclude an equivalence with the sigma type here. So here's what I want to do. I want to consider, so this is the next part. So we finished the embedding proof. So consider the fiber. This fiber that takes an element of the natural numbers, which I'll just call J here, and it returns the number added with M. So this is the same map we've been considering. And I want to consider the fiber of this map over little n. let me make sure I'm clear here. So for every M and N in the naturals here, I want to consider this type. What is this type? It's exactly the sigma type we want to consider, right? Okay, so to prove that we have an equivalence of M less than or equal to N with this sigma type, it suffices to prove that we have an equivalence with this fiber. All right, but how can we do that? So I want to, okay, let me just get a new page real quick. So I actually want to go, so it was good from the comments we mentioned that earlier that, actually, let me write it down where we're doing the problem. So we know from our remark before that N less than or equal to N is a prop. Also, this fiber is a prop. Why is that? That follows because we have a theorem from lecture yesterday that that if a map is an embedding, then all of its fibers are propositions. Okay, so also the fiber over N is a prop. So let's remember yet another result from yesterday's lecture. If we have, if we can obtain a logical equivalence between these two types. So if we have that, then we actually have an equivalence between them. Okay. So all we need now is a map back and forth. Okay, so we, all right, so to get a map back and forth, how would you, I'll ask I guess a final question. How would we obtain maps back and forth here? Or if you want, you can just answer the question for one of the directions and I'll fill in the other. What principle, method, technique do we have to try to get maps back and forth here? Well, in the interest of time, I'll just I'll say that let me write it here. Okay, so this follows by double induction on the naturals. So, you know, if we double induct on the naturals for all M and N, we'll get special cases for this type here. We'll have the unit type, we'll have the empty type, we'll have the for the double successor case, we'll have the previously defined type, and from those special cases we can construct pretty straightforwardly an element of the fiber, and then going back the other direction, it's pretty similar. It's also rather straightforward to do double induction and consider the special cases, and then construct an element of M less than or equal to N. So I'll leave that as a mini exercise, an exercise within the exercise. Okay. Okay, you know what? Like, so obviously, I've gone over the hour, but in the interest of recording this, and since it doesn't take too long, I want to do problem 4, but I just want to do one direction of it. Each direction each direction. Both of the directions are not too difficult, but I think one of the directions is more informative than the other. So I'll leave. I will leave the 4 direction that the first implies the second. So I'll leave as exercise. And then for the reverse direction, I'll do it here. So let's suppose that A times B is contractible. And let me name the center of contraction as S, which is, of course, an element of A times B. Note that I cannot assume that S has the form of a pair here. One second, is center. Wow, that's not how that should turn out. Well, you can kind of assume it's you can do some work to assume it's a ultimately you could do a proof that uses just the canonical elements A times B, but as of now we don't know that S is a pair. We just know it's an element to A times B. Okay, so now we want to prove that both A and B are contractible. Now, there are kind of obvious candidates for what the centers of contraction would have to be for A and B. If S is the center of contraction for A times B, then we really want to show that A, let me say, has center of contraction, the first projection of S, which lands in big A. So for every and then we also want to show B has center of contraction second projection. Okay, cool. So what can we do? Let's both cases are very similar. So let's just consider the second case here with B. Let's say, so let's let little b be an element of big B. And so all right, so what can we do here? We can we want to show that we have if we're choosing the second projection as the center of contraction, we want to show that the second projection of S is equal to B, where B is this arbitrary element. So how can we find a term of this identity type? Now, we can first consider the fact that we have an assumption that A times B is contractible. And then from that, we know we have a term. We have a term of type S equal to so we have a term that says that S is equal to this pair, right? Because since A times B is contractible with center of contraction S, any element of the product A times B will be equal to S, right? Now, from this, what can we say? Remember that A times B is, by definition, this sigma type over A, where this type family B is constant over A, right? So this is a special case of an identity in a sigma type. And we've characterized those, right? We know that from an identity here in the sigma type, we have that we have that well, let me write it. Okay, let me write it. To be precise, I should write it like this. So the I get so from this identity, I have a term that says that the first projection of S equals the first projection of S. Now we do know there's a reflexivity term, but from the characterization of identity types and sigma types, that's what we do. We get some term of first projection of S equals first projection of S. So let me call that Q. So what I then have for the second components is over Q. I can then take the second projection of S, and that will give me an equality with the second component B here, right? Okay, so what we need though is, now we don't want this transport here. We want just that PR2 of S is equal to B. Now, so here's the thing. This does in fact equal just the second projection of S. And why is that? It's because the what's going on here is that and the type family is B here. Let me use a new element. Let me just call this Y. Okay. So this is equal for all for any, and then for Y in B. So for any P in the identity type A equals A prime, and this is a property of constant type families. So B is a constant type family over A. So the transport actually is the identity function for each path that you plug into the first argument. Okay, so yeah, that gives us the second projection of S is equal to B, which is what we needed to prove that this is the center of contraction. Okay, so I thought that was the more interesting direction of the two. The other case with A being contractible is very similar, so I'll leave that to you guys. All right, I think that's all I want to go over. Any final questions on problem 4 here? Maybe problem 3 that I didn't ask. I didn't pause for questions at the end of problem 3 either. Anything for those two? Okay, so let me first stop the recording here. Let me stop. I need to stop sharing. All right, and let me end the recording now.